Okay.
All right. So Julia, thank you very much for joining us today to talk about Julia. We have sort of a talk inception here. I'm
Yep.
really excited about this talk. I'm sort of like recreationally a type theorist. Like I don't actually know type theory, but I know enough words like homotopy type theory to like get myself into trouble in a conversation. So I kind of enjoy these types of talks because they broaden the number of dangerous words that I know. So thanks for joining us. And
homotopy type theory is hardcore. I'm not there.
okay. And I'm going to give the floor to you. So take it away.
Okay, cool. Thanks for inviting me. I think today we're going to do a lightweight introduction to type systems in the context of programming languages research. So it probably will be more about lightweight intro and a bit less about Julia. But let's see. So I guess programming languages research as an area obviously has something to do with programming languages. But I like the definition that Mike Hicks gave in a blog post and in a talk, which is sort of saying that when we talk about an area of research, there are usually two sides to it. One is a set of problems and another is a set of techniques. So for programming languages, set of problems is something to do with the syntax, semantics, that is meaning, and implementation of programming languages. And on the other hand, there are a bunch of methods and techniques that have evolved during several decades of PL research, which are also applicable beyond programming languages and might be useful for some other areas. So it might be good to know for both sides of this. But specifically, we're going to focus on type systems, which is just one piece of programming languages research. And I hope we can make it interactive, although it's a small group, but feel free to ask any clarification questions or participate with voice, also with chat. I'll try to keep track of it. So the first question is, what comes to your mind when you think about types in the context of a programming language? Anything. I promise that there is no wrong answer.
I mean, I think about the compiler, right? Because the compiler has to like interpret what to do with the text that you wrote down, and types, from my novice perspective, seem like the most elegant and natural way for the compiler to be able to figure out in a deterministic manner what the hell you meant.
Yeah, that's a great start. I'm also curious for people who can say or type in the chat what kind of languages you're programming in, if any. Since I'm not sure what people exactly are doing for their research, but just curious what's the audience and what's the context. And maybe you can have some other ideas about types.
When I think of the word type, I think like int, float, string, and then maybe like a value type, like a wrapper or a struct or something. Just a way to organize a sequence of ones and zeros or bytes into something that has meaning.
Yep.
So I think, and just to answer your question, I think I'm not actually a PhD student. I'm just a software engineer. So yeah, when I hear the word type, I think, language constructs, things like that.
Yep. Yeah, exactly. Yeah, that's all right. And just to have some examples on the slides, types can definitely mean different things in different contexts. So compilers, for sure, they do describe how values are represented in memory, and they also used internally to do optimizations and stuff. But also on the design perspective, exactly, I think what, sorry, I don't know who was the last speaker, but talking about representing data, right? That's something we call abstraction. We also use types to even just to document what do we mean, because usually types are used to represent something in the domain that we write programs for. So there are many things that types can be used for and be thought of as. But today, specifically in the context of type systems and programming languages research, when we think about types, we often think about so-called static type systems, And you can think of languages like Java or Haskell, something where you have static types. And type system, the primary goal is to prevent some kinds of errors in a program before we go and start actually executing the program. And there is a very popular book called Types in Programming Languages by Benjamin Pierce. And what he uses to describe a type system is a lightweight verification technique, meaning you can, by type checking your program, you can prove that there are certain properties preserved by the program. And then if you're thinking of a type in this context, it sort of tells us what kinds of values this program can compute, what are legal operations, or what are the abstractions related to this type. So today we'll focus more on just talking about type systems. And because we're going to talk about PL research, there is a sort of hammer of PL research. If you ever open a type system paper, you will most likely see something like a table with a bunch of something that's called inference rules. So I'll show you the rules first, but what is this thing with this horizontal arrow? So at the top of the slide, we have this simple definition of a syntax with a BNF. If you probably are familiar with BNF, but the idea is just to tell if we call a program T, then how can this program looks like? So in this case, we say constants true and false are valid programs, and then we can write an if expression, and T is like recursively refers to itself. Right, so this is a BNF syntax, but we can use this tool of inference rules to define the same thing. And the idea is we'll be describing what are the programs or terms that belong to a set of valid programs, the squiggly T. When we don't have anything above the rules, we just say this is a fact, like true and false are programs. And another way to build a program is to use this if expression where condition and branches are itself well-defined programs. So usually the way to apply the rule is we'll look at the bottom, find a rule that sort of matches the structure of something, and then check the premise. So we call this bottom conclusion, and what's above is a premise.
So Julia, just to be very clear, you're presenting three rules here. One of them is that true is in the type T. The other is that false is in the type T. And then the other one is this inference rule or judgment below, right?
Yep,
and
exactly.
So if we were being like super explicit and using something like regex, we would have a line above the true in T, a line above the false in T, and then a line above each of the requirements or whatever you call them that are in the third rule, correct?
Right, yeah.
Okay.
Yeah, this is a simplification without the horizontal line because it's a screenshot from the tuple book. Yeah, but
sure.
You're
it's
right.
like syntactic sugar or something.
Exactly. Yeah, this is just saying we don't need to require anything. We can just say that false is a valid program. And just as a warm-up, a couple of examples. So if we write something like a true, right, we know that this is a valid program because we have the rule. True belongs to valid programs, and then the if statement, we can match it with the inference rule and check that all the premises are also valid. But then these other examples are not syntactically valid programs because we cannot match. So in particular, in the case of this second example, although the outermost structure looks similar, when we try to check the premise, we won't find a rule that tells us that this true thingy is a valid statement. Okay, so that's sort of just a mechanics, the tool that is going to be used throughout the talk to define several other things related to programming languages. And well, often when we look at the research papers about programming languages, there should be some way of defining what language are we talking about, and at least two things that usually are there. Well, first is, of course, syntax. If you don't know how to write a program, then how do we know, like, what is it? And then the other thing is semantics, or semantics is a meaning, right? And there are several ways of defining this meaning formally. We'll look at just one of those. But the intuition is just we need to have a way of saying, what does this program mean when we write it and try to understand, right? What is this program doing? So usually it's important for programmers who write in a language. They have some maybe a language manual and they roughly have an idea of what each construct means. So they have an idea of what's happening when they write this program. So formal semantics is just a formal way of describing this. So for example, here it's just some simple Python program, and the question to the audience is, what do you think, what does this program mean? Or maybe what does it do? And okay, I guess I'm assuming that people know Python, but if you write in any programming language, this is just a function, right? This is what it computes for the argument x, and this is calling a function. So
I would imagine that with like a reasonably naive Python, compiler that we could actually write down on paper, this would literally compile down to just the term, which is the number 5, right?
Yeah, exactly. Right. Eventually we know that this thing should compute number 5. And this is the interesting thing that you said about the compilers. There is a distinction which is often made between compilers and interpreters. And roughly the idea is, when we talk about the compiler, we have a program in some programming language, and then we take it and transform to some other language. For example, it can be maybe native assembly, or it can be some intermediate representation, right? So compiler transforms program from one language to another, but then eventually we need to say what is exactly happening when we are running the program in this, say, final representation. And for this, one way to do it is to define an interpreter, which explains how to take the program structure and compute it. So essentially, today we are thinking just about syntax and interpreter. We're not going to talk about compiler a lot. And as I said, there are multiple ways of defining the semantics. It could be, for example, the notational semantics, which used to be quite popular in early days of PL research. Nowadays, interpreter style, or this so-called small step operational semantics, is a bit more popular. And the idea is we want to define a sort of a state machine to explain what happens in time when the source program executes. Another way of thinking about this, if you're familiar with writing rules, we'll take the entire program and then we'll transform it step by step until we reach the result. So the rules for small step operational semantics for this simple language that we had with just true, false, and the if statement. Again, we are using inference rules, and here the idea is we are saying what are the ways to rewrite the program on the left of this arrow to the program on the right. And the idea is we are going to simplify the program by applying these rules. Right, so here, if we know that the condition is true, well, we are going to take the first branch, right? And then what may be the more complicated rule, when we have a program, which is an if expression, but the condition is not yet either true or false, so we don't yet know which branch to take. What we first need to do is to simplify the condition. The premise of this rule is we'll first try to run this conditional part of the program, we simplify it, and then we replace the simplified thing in the condition of the entire program. So we are rewriting the entire program step by step, but to do this, we need to look at the sub-expressions. And just again, as a warm-up, we can try to run this example. So here we have an outermost if expression, and the condition is itself an if expression. What do you think would happen with this program if we try to apply one of these rules? I hope this makes sense. Let me know if you have any questions. Inference rules are a bit tricky.
So Artem and I both know the answer, so maybe somebody who doesn't know the answer should should give it a shot.
You can also ignore the rules and try to apply your just programming intuition, right? This is if you see this program, like this is just an if expression that you would write in could write in most programming languages, and you should have some intuition about, right, what happens to this program when we try to run it.
Well, I don't know exactly the rules that would happen, but I'd hope the first set of parentheses would just evaluate to false, and then you can
exactly
simplify from there.
Yep, that's exactly right. Yeah. So here, right, we have this big if expression, and the condition is not yet in the form true or false. So what we have to do is to try to run the condition. And then when we look at the condition, obviously it evaluates to false by one of these other rules. So then the entire expression, if the entire large if expression is replaced by a smaller if expression, right, where we now know exactly what's the conditional, and we can go there. Okay.
Sorry, can I ask a random question?
Yeah, sure.
If it's foreshadowing or something too broad for this talk, that's totally fine. But I'm curious about when this simplification works and how long it takes, because it feels like if this is just something that magically works for us all the time, then we don't really worry about Boolean satisfiability and a whole bunch of other NP problems. Or maybe I'm missing something.
I'm not sure exactly what you mean. The way we apply the rules is we just look at the program, and if it matches at least one of the rules, we can apply it. If it doesn't match, then this is so-called stuck state, or you can think about this as a dynamic error. So something wrong happened, and we don't know how to evaluate this program.
Okay, so there could exist some statement that takes a really long time to reduce or can't reduce, for example. I guess that's sort of my question.
Okay, so if we abstract from this particular example, in principle, you can have rules that, for example, will lead to non-termination. So you will always be able to apply a set of rules and get to the same state that we started with. Max posted an example, which is called omega, which is an example of a non-terminating program. So there are definitely, if you pick certain set of rules, then you can definitely just get a situation where you never reach a state that is no further reducible. So you will.
I would say it's not only a set of rules, but the language, right? Because here with ifs, you can't really do anything like lambda x, like whatever Max put on the chat.
Right.
Yeah.
Okay, thank you. That answers my question.
I once drove Amal slightly nuts in class by trying to get her to answer the question of whether or not Gödel's incompleteness theorem could be rephrased as a theorem about how there always exists a stuck term in any Turing complete language or something like that. And I feel like it's morally true, but I'm not quite sure how you'd prove it. But that's kind of what you're getting at, Jacob, is like you basically, for all intents and purposes, in anything that's remotely useful, you're always going to have some stuck terms that you can't compile.
Yep, I'm not exactly sure whether it's true or not about the way to express this, but sounds somewhere in the ballpark.
It's an interesting question, but I don't think it's directly what you're saying. Like the incompleteness theorem is exactly like not being able to reduce something, because incompleteness means you can't prove some true facts, right?
Right,
so
you're right. There is a difference between the existence. Yeah.
Yeah, that would
totally
be a program that reduces to true, but you can't find a set of reductions that lead to it.
Right. So the compiler problem is strictly harder because you have to deterministically produce the proof, whereas in Gödel's theorem, it's like there exists a proof, but that's a different statement. That's less difficult than like we have a procedure that will give you a proof. That's an interesting point.
Okay, so let's see. I'm going a bit slow. Let me try to speed up a little bit. Right, so what we've seen so far is 3 simple rules that tell us how to rewrite the entire program and get to some final results, such as just true or false in this case. And I guess one thing I want to mention is that here our states are entire programs, but in principle, if you want either more efficient implementation or you have more features in the language, like heap and memory allocated objects, then your state would be more complicated. Or maybe you can have a stack and a heap in it and stuff like that. So this is a really simple example. But now let's imagine that we have a slightly more interesting language where we also have integer numbers, right? And we have the same, still we have the same 3 exact rules. And the question is, what happens if we put a program that evaluates to 42 and 42 ends up in the condition? And then for this example, the answer really depends on the programming language. The rule is different if you're in JavaScript or Python. They might choose to interpret anything as a Boolean. So this might work in some languages, but in principle, there can be illegal operations for certain kinds of values. So in maybe non-Python and JavaScript language, most often you will get a dynamic error. And formally, this happens because we don't have a rule that allows us to run the program which has 42 or integer value in the conditional position. Right here, we're only allowing true and false. Otherwise, we can't reduce this program anymore. So this is an example of a dynamic type error. And the goal of a type system is to prevent such silly errors. The idea is that instead of running a program, we can somehow approximate the behavior of the entire program by ascribing types to parts of a program, right? We can look at the program and try to imagine what will it eventually computes to. So with this simple example, we'll say we'll have just Booleans and integers, and if we have a program that's already a literal constant like true, false, or an integer, then we can directly say that, oh yeah, we know for sure this is a Boolean, right? Or this is an integer. And then what's a bit more interesting, if we have an if statement, well, first we know that our rules only allow for Boolean values in the conditional position. So we know that in order for this program to successfully execute, at least we have to know that the conditional is a Boolean, or the conditional will evaluate to Boolean. So that's one requirement. And then we also want to know that the branches will do something reasonable. So we can approximate them with some type. And then we say, well, if we know that both branches will evaluate to the same kind of value, then we know that the entire if expression will evaluate to this kind of value. So this is a static approximation of a program behavior. And again, we are using inference rules. So before we use them for describing dynamic semantics or like rewriting rules. In this case, we are defining a judgment or a predicate. It tells us that a particular program and a type are in this relation of well-typed programs. Or you can think of it as just a predicate that this term has this type. Right, and then the idea is we use the rules in the same way as we did with built-in syntax. So if we have a program and we want to type check it, we need to find, we look at the structure of a program and find what are the rules that match the structure. So for example, in this good case, we see that this is an if expression, right? So we have to check all the premises. In this case, all the premises are successfully type checked. So we can assign a type to the entire program. And we know that this program will successfully execute. And then the problematic case from the previous slide where we had 42 in the conditional, this thing will not type check because again, we know that we have to have a Boolean in the condition. And since we don't have a Boolean, we say, well, there is no good typing that we can ascribe. So we cannot predict good behavior for this program. And then type checking is compositional, meaning that we look at the big program and then we look at subprograms, and if subprograms type check, then we can say that the entire program probably type checks. But if some components are not well typed, then the entire thing is not well typed. So we require that all the pieces of the program are can be statically approximated. Which means that although in this case we did rule out a bad program, right? This one we know had 42 in the condition, and then it errored dynamically. But because we are doing the static approximation, it means that we'll also have to conservatively reject some programs that might be at runtime actually completely benign programs. So I have two examples here. One. So here in this if statement, what we do, we return different types in the branches, right? So this program itself is completely fine. It will not run into a type error, but the problem is because it returns different types, and we have such a simple type system where we only have Booleans and integers, we don't have a way of describing the behavior of this program. So in our simple type system here, we require that both branches have exactly the same type. And when they're not, we say, well, sorry, we don't have the power to predict what this program does. So this is one thing. And another thing is if the program doesn't run into an error at runtime, but our static approximation says that it might. Like in this other example, we only take one of the branches of the if statement, and one of them is the bad branch and another one is a good branch. But if we don't have a way of knowing without running a program that this other branch will not be taken, we have to conservatively assume that bad behavior might happen at runtime. And what's important to note here is that there is a balance between expressivity of a type system, right, and sort of the usefulness of the type system. Clearly, there is a very silly case. We can say that we can make a type system that doesn't type check anything, like it rejects all the program. Right. In that case, well, we never run into bad behavior, but this is a completely useless type system because we cannot write a single program. By making type systems more and more complicated, we can reject more bad behaviors and we can allow for more good behaviors, so that we can write more interesting programs and still have some guarantees from the type system. But this is a complicated process, and the more complex your type system becomes, the more involved the process, and maybe it takes too long to compute, or maybe it's even undecidable, like say Scala type system, which means that in principle you can write a program such that your compiler doesn't terminate because it just doesn't know how to handle with the type system. So this is a balance that real languages have to maintain, and sometimes they need to choose, maybe I really want these interesting features that are super useful in some cases, but then we have to agree that sometimes programmers will run into undecidability in the compiler. Or if you really want decidability, then sometimes you have to make your type system simpler, and then you have, as a user, you have fewer options how to write good programs. But on the bright side of this complicated story is that when we do have a static type system and our program type checks, and it's a real static type systems with guarantees, I'll say at the end, I just mean not something like TypeScript or Python 3 type annotations. So when we do have a real type system, it gives us a strong guarantee that if a program type checks, then we know for sure that at runtime we won't run into some set of dynamic errors. And in formalization, we always say exactly what kind of errors we rule out. So in this case, right, we just rule out bad if conditionals. But for example, if we have a division by 0, then this error still might happen. This is not something that type system rejects. On the other hand, you can have more complicated type systems, that so-called dependent type systems, where you can rule out division by 0, but maybe you cannot rule out some other things. So this is a whole huge area of research with different kinds of type systems and different things and different kinds of bugs that you can rule out. If you think about Rust, this is more like, this is another kind of behavior where we rule out bugs related to memory. Right? This is, again, some approximation of runtime behavior and a way to rule out certain errors that might happen at runtime. Okay, but coming back to our simple story here, we'll make it just a little bit more complicated. And the thing is, most programming languages that we write have functions. And formally, there is a thing called Lambda Calculus, which you can think of as just a tiny functional language, which just has functions and applications. So this is the traditional syntax for Lambda Calculus, but what it really means is this lambda x.t is just a function definition with an argument x and the body t. And t space t is a function application, or you can think of a function call. Usually we call it with parens. Right, and then oh, maybe actually let me make it a question. When we call functions, what does happen in our mind with a program? Right, when we just, what happens when we call a function? Like what is the meaning of this? And I apologize if I got carried away too much talking about different type system, but now we are back to the simple story. It was just simple types and simple programs. Here we just have functions and function calls.
I guess as a more applied programmer, I would think of this as, oh, in a compiled language, it probably ends up as some type of assembly somewhere, like maybe there's a jump to it and it jumps out. I don't know if that's what you're...
I mean, this is definitely just another way of describing it. But what else happens when we're jumping to a function?
I guess if you're talking x86, you can say you're calling something. You're putting arguments onto registers or the stack.
Yeah, yeah, exactly. That's what I wanted to hear. Indeed, right. The main thing that happens when we call a function, we have to take the arguments and put it right. And if it's a stack, we put it in a stack. Or in this case of our small step semantics, where we use rewriting rules, what we do, we just literally take the function body. In this case, it's lambda x and then the body, and take the argument and replace variable with the actual argument in the body. So this thing denotes substitution. So if in this case, we'll put some integer instead of x in the body and continue going. Right, and then this first rule just says, so we didn't talk about values b, but it's a subset of programs that describes computed irreducible values. So this could be integers, constants, or when we have functions, these are function definitions. And in order to call a function, we first need to compute an argument, if this is not a lazy language, which most languages aren't. So in this simple example, does anybody want to say what happens using these rules? So in here, we're just calling function foo with arguments 3 plus 5. What would you expect to happen to this program? Again, I promise this is completely straightforward. You know what happens.
I would hope that it would first simplify the 3 and 5 to be an 8 with maybe some of the rules we talked about before, and then call it.
Yeah, exactly. Right. Yeah, first, because we don't have a fully computed argument, we use like this arg rule to compute the argument. And then we take the body of the function and replace x with 8 by the second rule. And then finally we'll compute addition. Yep, you nailed operational semantics. Okay, so now we are back again, right? Currently we don't have types in here, and we can run into some errors at runtime. So this is a real Python example. Here we have this function, same function foo, which computes x plus 2, and then we're calling it with a string. Right, we can totally do this, but then if we run this program using our rules, well, we'll first take the body, replace x with a string, but then there is a dynamic type error because Python will say, well, you cannot concatenate string with a number, right? This is an illegal operation for these types of values. So this is a dynamic error, and it would be really nice to rule it out before we run the program, because it's, well, obviously it's going to run into a type error. So any ideas, how can we do this by using types? What do we need to, what do we need to do about this function, for example, in order to prevent this from happening?
You maybe need some constraints on the input argument.
Yep, exactly. Right. So one way to describe constraints is by just using this type annotations. So if you're maybe in a language like Java, or I guess this is not Java syntax, but in some statically typed languages, we can put a type annotation to say, this function only works with arguments of this type. And then the type checker will check that indeed this is a legal operation, assuming that the variable argument x has type int. So it will say, yes, your foo function is good. And then if we call foo with 42, it's obviously good. But then when we call it with high, the type checker will tell us before we run the program that this is a bad program. We don't want to allow it. And then formally, we are going to use the inference rules again. And the structure of this typing judgment is similar to the one that we had before when we just had if expressions. But it needs to be a bit more complicated. Namely, we have this thing called gamma is a type in context, and it just keeps tracks of types of variables. And if you're familiar with some maybe logic or something like sequent calculus, you can think of this as a judgment where gamma has assumptions, right? And on the right of the typing judgment, we have a conclusion. The meaning is still the same. We want to say that given assumptions, some program has this type. And yeah, this is a bit too much of symbols. Let's just focus on maybe application rule. So what is this saying? It says if when we have a function call, right, and we know, well, first we know that the left of the function call is indeed a function, meaning it has this type with an arrow which says I'm a function which takes arguments of this type and returns arguments of this type. And if I call this function with a good value of the exact same type, then we get the result of a function back. And then this context gamma is it's really needed just to keep track of function arguments. So in our running example, if we are type checking the body of this foo function, we know that like currently in the context we have variable x of type int. And then we have to check that x plus 2 is a good program. In this case, plus is allowed for integers, so we can type check it. And for those of you who are in logic, if you look at this application rule again and just sort of cross all the T's and yeah, imagine this, it's saying just gamma, T1, arrow, T1, 2, right? And then we have this argument, and then we have the result. This is really the modus ponens rules. This is like just an implication, right? If we know that something like A implies B, and we know A, then we know B. And here there is a fundamental connection between type systems and logic, which is sometimes referred to as propositions as types, meaning that when you have a proposition and logic in some in some specific logic, right, there is often some specific type system which has types that correspond to propositions, and then proofs in logic correspond to programs of these types. Yeah, so this is a fun fact. Okay, 43 minutes. Okay, let's see. I'm gonna skip some part about Julia, but let's try to recap a bit and talk just a little bit about Julia. So we talked about formal ways of defining programming languages. Namely, we talked about runtime semantics, right? This is a way the way of defining how program executes at runtime. We talked about types and legal operations, and we know that sometimes we just don't know how to deal with something like a string plus integer. This is a nonsensical operation. And in dynamic programming languages, these kinds of operations usually end up with a runtime error. So you have an error, but it happens at runtime when you run the program. So when we talk about languages with static typing, the idea is we want to statically approximate the behavior of program and predict what kinds of values it's going to compute. And then by knowing these approximations, we can statically, without running the program, we can rule out certain bad behaviors. So in this case, since we know that this program only works, this function only works when it's called with integers, and if we try to call it with something that we know for sure is a string, we know this is not going to end well. So we can rule out this program before running it. And this often happens in compiled languages where we have this first static checking, right? Before we actually run the program, it has to pass some checks and maybe be compiled somewhere. You can see this in languages like Java or Haskell. And one thing to note is that statically typed languages don't have to have type annotations all over the place. Sometimes you have type inference, which looks at the program and infers these annotations automatically. And this happens in often happens in function languages like Haskell, SML, or CAML, stuff like that. And even in Java nowadays, you don't need to always write type annotations everywhere. Some pieces can be inferred by just looking at the program. But behind the scenes, you still have this static information about program and types that describe the behavior of program. And then the compiler can check that these behaviors are that they're good and they will not run into the error. Okay, so quickly about Julia. Julia is a language for scientific computing. It's a dynamic programming language. And from the first glance, you can have functions like in Python. You can write a function without a type annotation, like this one, x plus 2. And then if we call this function with a string, we'll get a runtime error. So far, it seems pretty similar to Python. However, what's interesting about Julia is that you can actually write type annotations in function definitions. And these type annotations are not like in a statically typed language, but they do matter for the semantics. So no static type checking means we can still call this foo high. And we will not have a compiler that tells us, this is a bad program. But when we run this function, which had an integer annotation on its argument, what's going to happen is we'll get a different kind of error. It's not going to be a type error like in Python. Instead, it will tell us, you know, you don't have a function implementation that can work with strings. So you defined foo to work with integers, and you're trying to call it with a string, and that's a bad idea. So we still get a runtime error, but this is well, first it happens earlier. We're not going to enter the body of this, the definition of the function, right? And it does know the types at runtime, and it prevents us from calling this foo for integer with a wrong argument. I'm going to, okay, I will skip some parts of this, but the way it works in Julia, it's called multiple dynamic dispatch. And the idea is that all functions in Julia can have many implementations for different types of arguments. Because Julia is a language for scientific computing, it's actually super important that you can use the same symbol like plus for numbers and matrices and whatnot, and you can define efficient implementations for different kinds of data, and then just use the symbol like in a paper. You just have this math formula, which actually is a program, and it runs. And what happens when we call a function, what happens is we look at the types of the arguments, and we look at all the available implementations, and we pick the ones that have the best matching types to the actual types of arguments. So at runtime, in this case, when we call a function with the floating point numbers, we will find that there may be multiple definitions that in principle can handle this call. For example, number is something that is sort of larger than a float. Numbers include floats and integers and unsigned integers. So in principle, this definition can work. It would be fine, like maybe it will not run into an error. But the definition for floating points is specifically designed for floating points, so it's the most efficient one. This one will probably call the native implementation of floating point addition. So at runtime, we'll look at the types and pick the best suitable implementation, which will be most specialized to this kind of call. Right, so that's the idea. Every time we call a function, if there is a method that can handle our kinds of data, then we'll call this function. If there is no definition, like in our previous example here, since we don't have a definition of foo for string, we'll get an error. Okay, and does this make sense? Okay.
Makes sense to me.
Thumb up. Okay, so then let me skip a bit the internals about how exactly that works. And just to emphasize this point that we can write type annotations and functions, and we can have multiple definitions for different kinds of data. And what this means is that we are only allowed to call these functions for the arguments that we specifically said we are supporting, right? Unlike in Python, you cannot, if you have type annotations, they actually impact this dynamic semantics of a program, and you are guaranteed to have a value of the specified type when you are inside the function. If you ever like saw TypeScript or Python 3, which has type annotations, it's something that's called optional typing. And the thing in those languages is that even though you can write type annotations and some static checker will try to tell you if you have an error, you're not guaranteed to have a value of the type you're specified at runtime, because those systems are sort of bug finders. They can help you find bugs, but they do not provide guarantees. So you can still, in TypeScript, you can still, even if you have a type annotation, you can still get a string here. Maybe because your program was too complicated and the compiler wasn't able to figure out that like the string ends up getting to this function call. So you're not actually guaranteed anything from this type annotations in Python or TypeScript. But in statically typed languages and in Julia, if you do have a type annotation, then you are guaranteed to have a good value of this annotation type at runtime. And that's super important for the semantics, and right, and what kind of, as a result, what kind of things the language implementation can do. So namely, if it knows that this is an integer, it can, for example, optimize this addition because it knows how to most efficiently add integers. Whereas if you're in TypeScript, even though you have this annotation, it actually doesn't mean anything for runtime. So you cannot rely on this. This is not an assumption that's valid at runtime. Okay, so this brings me to the end. So just to recap what we saw today, we talked about dynamic and static typing first, right? Dynamic typing is when we run programs that are syntactically valid, but we don't try to rule out bad behaviors. So we just run the program, and then if we apply an illegal operation, we just get a runtime error. On the other side of the spectrum, we have static typing like Java or Haskell, where we either use or infer type annotations. And the compiler statically approximates program's behavior. And if it thinks that this program might run into a type error, then it rejects it statically. So you're not able to even run it. And this trade-off with static type systems is that they provide guarantees and rule out bad programs. But on the other hand, sometimes you're not able to express good programs because they are because type system approximates, sometimes it has to rule out programs that are actually fine. But again, you get guarantees and you're guaranteed to not run into a type error at runtime. And then depending on the complexity of a type system, you can rule out more bad programs and allow more good programs. And then we talked about Julia, which is an interesting point in the spectrum. This is a language with so-called dynamic dispatch, where we use type annotations to specify which kind of arguments are allowed in the implementation. And there can be multiple implementations for different kinds of arguments. And if you at runtime, right, we don't do static checking, but at runtime before calling a function, we actually look at the argument type and pick the best implementation if it exists. And if it doesn't exist, this is an error. And why I have this squiggly arrow here from dynamic dispatch to Java, if you're familiar with object-oriented languages and inheritance and something like virtual functions in Java or in C# and then some other object-oriented languages, there is actually a form of dynamic dispatch in those languages when you define a function in a base class and then redefine the definition of a function in a derived class, right? If the function is virtual and we call this function, we don't know statically which class is it. If you have a variable, it can be statically approximated, but because of inheritance, sometimes we don't know which exactly class is in this variable. So then only at runtime we'll pick the right implementation of either original function method definition, I guess, method, or its override definition based on the runtime type of the variable. So that's very similar to dynamic dispatch in Julia. Like the only difference is that in those object-oriented languages, we only look at the type of the receiver, right? It's like x dot method, and then we only look at the type of x. Whereas in Julia, we can look at the types of all arguments, and they're all completely equal. So I think that's all I have, and I'll be happy to answer any questions or discuss something about compilers, interpreters, programming languages, and type systems in general. And thank you.
Thank you very much, Julia. I have questions, but I want to let other people ask first. Jacob raised his hand. So Jacob, why don't you take it away?
I'm also happy to let other people ask first since I had talked a lot. So I appreciate this summary slide at the end. That's really helpful for me. I'm curious sort of what you would say. So one thing to mention, I don't know a ton of Julia. I do know that it is a Lisp. And a lot of Lisp language people really like their dynamic types, and they'll say things like, oh, you can't have all these static types when you want to do all this fancy metaprogramming type things. Would you say that dynamic dispatch is a good idea for them and sort of a step forward and this thinking is outdated, or in their own context, do they have a point why dynamic typing would be better for metaprogramming?
So let me try to unpack here. So in principle, metaprogramming does not have to be limited to dynamic languages. There are like ways to support metaprogramming in languages like Haskell, where you still try to check the structure of a program. So maybe I should say that metaprogramming is when we write functions that operate on program representations. So we can, for example, the typical example is, say, you can generate a program that takes the value of a power and generates, like if it takes 2, it just generates x times x, right? If it's like, regardless of the number of power that you want to put your number in, you can, in the language, you can write, say, a for loop, which generates a representation of a program that does times this number of times, which calls multiplication this number of times. So metaprogramming is when we are generating a program in our language using this language. And because it's like reasoning about code is hard, I think it's easier to implement metaprogramming in dynamic languages because you don't need to type check them, right? You don't need to statically figure out what is this for loop that generates a program, like what is this program that's been generated doing, because it's harder to reason about program generation. So definitely languages like Racket or Lisp have great support for metaprogramming, and Julia. So Julia itself is not like Lispy, although dispatch, like Lisp, some was it common Lisp had dispatch too, but Julia does inherit a lot of metaprogramming support. I don't think that dispatch specifically makes it much easier to do metaprogramming. I guess you can have metaprogramming in other dynamic language too. And it is harder to do metaprogramming in statically typed languages if you want to still provide guarantees about programs that have been generated, but there are ways to do it.
Awesome. Thank you for unpacking like the 10 different things that were implicit in that question. That's great.
Okay, cool. I'm glad.
What, sorry about this. What is a Lisp? Can you give a quick, I know it's not within the context of your presentation, but just so that I can understand what it is you just said.
Yeah.
What is Lisp, but I guess.
Yeah, Lisp is one of the early programming language. Like it's famous for using a lot of parens. Essentially, what's interesting in Lisp is that sort of everything is data, including the program itself. And all the programs are essentially just either literals or lists of things. Like a function can be a list of arguments and the definition, right? Or a list, or like a vector is maybe a list that starts with a symbol that tells you that I am a list, and then has elements. And because of this unified representation, it's easy to write programs in Lisp because you can also say that, well, my abstract syntax tree of a program, like say, I am a loop, and here are all the pieces of a loop, or I am a function, here are arguments, right? So Lisp has this unified way of representing data and code and operating with code. So it has nice support for this metaprogramming where you can generate programs that do something. Lots of irritating, stupid parentheses. Yes, yeah. Some people don't like parentheses at all, and it's yeah, it has its upsides and downsides. And the upside is because of the unified representation. It's sort of easy to write programs that operate on programs because you always know that the structure is like list head and a bunch of things.
Gotcha. And so one more thing. So when you use the word program, do you mean like, a program with an entry point that can be, called by an operating system and passed some arguments, or do you just mean like a collection of symbols that compiles into something, like a function or a list?
Right. So okay, I guess it's a collection of symbols. Depending on which language you're in, it may be compiled, or if you're a dynamic language, maybe like Python, it may be interpreted or compiled at runtime into something. So the when we write meta programs, right, we have some code that I guess has an entry point, and we enter this entry point, and then we executing something that builds another program representation, and we can say to our language environment, well, now you can please take this code that I've generated and load it, and once it's loaded, you can call to it. So you can define, and maybe you have a like you have a plus function that works with 2 arguments, then you can generate a new function +3, which calls twice to the original plus, right? And then this new program is loaded, and after it's loaded, you can call your +3. So even though you didn't write +3 in the source code at the beginning, you've generated this during program execution, and then in the end, we can now use this new function.
Okay, gotcha. Thank you.
Thank you for great questions. That's very fun.
Julia, with dynamic dispatch, how do you, maybe you said this already, if so, I apologize, but how do you handle something like if false, return foo of high?
This will fail, you said if false.
Like the type error happens after a condition that will never be satisfied, basically.
Right. If it's not satisfied, you will like if you don't enter bad branch at runtime, you just don't have any errors, right? So with the dynamic dispatch in Julia, where we don't have any static checking, like if program actually never reaches bad execution path, then you're good. Like this program will not be rejected statically.
Got it.
Yep. Yeah, with languages like Java, right there, you will have like you still have your static type system that will reject this kind of program, but then you just have a bit more flexibility at runtime, which implementation to pick.
I had a question about this this table on this last slide. So Python seems to be the most dynamic out of these 3 examples, but it still says dynamic typing, which formally speaking looks like suggests that there is some kind of typing there. And the question is there anything less typed than Python?
Right. I think, yeah, this is a tricky question from PL people, right? I think the difference between dynamic typing and something worse is when you ignore the original type of a value and try to reinterpret bits in a memory in the way that can work. So this, when we are thinking about languages like C, there, even though sometimes it seems like we do have some, right, we do have maybe some type annotations and maybe something will not work, but you can take your integers, right, in a variable and consider, or maybe you have an array, and then you can use this memory and try to use it as a different type, like a float, and you can corrupt memory, and some weird stuff will happen at runtime because you're manipulating these memory bits, ignoring original intentions about the values. I think this is the only thing that is sort of worse than dynamic typing. With dynamic typing, at least we, although we also, like when we're in JavaScript, right, we often will sort of convert values, maybe of strings, to, we'll consider non-empty string to be a true value, and empty string to be a false value, or something like that. So even though we are reinterpreting values in different types, at least we are maybe not manipulating the memory directly, something that we can do in languages like C.
Cool.
I wonder if that's the answer that you hoped for.
Yeah, I had one thought that you mentioned that something worse than Python. I wouldn't say it's worse, it's just crazier. But some people like it, right? So, and some people may be more efficient or more productive in this kind of environment when you can do crazy stuff with, right, like reinterpreting integer to pointers to functions or something. So yeah, but yeah, that's right.
Yeah, I guess just further, on the spectrum.
Yep.
I'm sorry, my dog is freaking out in the background because of a squirrel. But I think we should probably wrap up because we're pretty far over time. So I don't know if anybody has a last question they want to squeeze in before we call it a day. You hear the dog?
Yeah, I hear it.
Yes, the dog has a question about types.
Yeah, about the squirrel type.
Exactly. All right. Well, thank you very much for the discussion, the fun and the fun questions. Yeah.
Hey, thank you so much, Julia. This is great. Really appreciate it.
Thank you.
All right. See you guys later.
Have a good evening, everybody.
Bye, everyone.
Okay, bye.